Thank you, and welcome to my presentation regarding using novel infrared sensors for contextual intelligence. Here mainly detecting the speed, the distance and direction of movement of a person in confined spaces. So the motivation of this project is actually a gap in current building management systems, which is the missing information required to effectively control the different elements, such as HVAC systems, controlling the light, turning it off and on again, depending if people are inside the room or not, and the blinds, for example, with the ultimate goal of reducing the power consumption, the energy costs, and the carbon footprint. And while working with this, with STMicroelectronics, we had the privilege to work with them, we got in touch with a new sensing technology, which is an infrared sensor, the TMOS sensor, and it could not only enable us to achieve this goal of contextual intelligence, but also push the technology from classical approaches to be like kind of flight sensors and cameras that generally work in milliwatt range to a completely new range, which would be the microwatt range, which would enable us also to create, and this is what I'm going to show you as well, a completely self-sustaining device for contextual intelligence. So the TMOS sensor is actually, and works on the same working principle as pyroelectric passive infrared sensors. So the sensors that you generally find that turn on and off the lights depending if there's movement action. But there is one critical difference. The main one is that it senses the absolute temperature, so it can also detect the presence of people instead of only being sensible to movement. It also features an ASIC that performs the very first steps of data amplification, data filtering, and also some embedded smart algorithm that I will show later. And this is generally not the case for PIRs, where you have your own circuits for that, the analog front end at least, which of course in turn can actually increase the power consumption. And the last point is that it does not require any kind of lenses to work properly, although you can add them in order to increase the range and change the field of view, which in the case of the PIRs, you have these very typical faceted Fresnel lenses. So here's an internal view of the ASIC. I don't really want to talk about everything because you more information in the paper, but I think important is what I'm highlighting right here, which is this part of the amplification and filtering, which is already done by the ASIC, besides some very nice features, which is this embedded smart algorithm for presence and movement detection. This means that the MCU can actually be completely turned off in a deep sleep state and only be woken up when there's an actual movement or presence detection. So you can imagine that you can actually really reduce the power consumption of the system. So they promise more or less 10 microamps at 1 hertz. So at the beginning, when we started, this sensor was in its first initial stages of development. So there was little known about it. So we had to do a full sensor characterization. So basically understanding what happens with the signal when someone is tackling in front of the sensor at different distances, at different angles. And this is what you can see on the left, right? Which is the angle dependency. So if you have a different angle with respect to the sensor at different distances, you see this Gaussian pattern. Without lenses, more or less one field of view of almost 80 degrees. We generally use lenses to restrain it to 30 degrees, which I will show later. And in the case of the TMOS distance, you can see there's a pretty neat exponential pattern. And by looking at the log, you can see that the noise increases with distance, which is kind of expected. But here you can see that the actual limit of the sensor technology without any lenses is more or less 4.5 meters. So here, I'm not really showing the 4.5, but you can really see that it's kind of divergent, right? And we use this dependency also to get a full spatial dependency. So basically, we know exactly, or we can estimate more or less what the sensor signal is going to be at basically any position of a person with respect to the TMOS sensor. We use this information in order to estimate direction, speed, and distance in confined spaces. And the reason why we restrain ourselves to only these 3 pieces of information is because these are the building blocks for more complex devices, like for people quantum, which I will show later, also for individual workplace occupancy, which is growing very fast in the building systems, and also flow estimations. So how we approach this is really going for the minimal configuration possible, which would be one sensor. So here is actually one construction that is not really possible and not what we're really using. The reason is because the sensor is actually symmetrical. So basically means that if you have someone walking to the right and left in front of the sensor with 90 degrees between the movement and the course increases because there's no temperature in the field of view, right? So one solution would be to tilt the sensor by 45 degrees, and this is the approach that we use right now. So you can really see that we created some discrepancy in the signal when someone is going to the right and then going to the left, just by comparing the gradients before and after the peak. And this is part of the feature space that we're using. So we not only use the gradients, but we also use the height. We use the time between the peak width, basically. And this is mainly for the speed estimation. So just an example here for the TMOS speed, you can clearly see that if I only take the inverse of the time, you can clearly see a correlation with the speed, with the actual speed. And this is basically just a linear pattern, right? We not only use the peak width, we also use the height, but still you can clearly see that only this information is more than enough to get a pretty accurate system. So here's a resumed version of what features we use for each estimation. And I think the interesting part here is, at least for everybody who thought there would be some kind of machine learning involved, this is not really the case. You can actually really go with simple regression. And this shows actually the potential of the technology because it enables us as developers to create very low power systems because we don't need any process overhead, right? You can go with simple regressions. And just to show you with a simple prototype that we wanted to see if it actually works, because this was on theory for now, to create and use a very simple development board that I created before that only includes an MCU and also includes only the energy harvesting part. So there's nothing more, only an MCU, the energy harvesting, since I showed that it's going to be self-sustainable, and a super cap as a backup. And then just connected it with the TMOS sensor, a solar cell in the back, and that's basically the system. Before I show a very small demo for people counting, I actually want to show the results. Probably you want to know how good the system can actually perform with simple regressions. So here is the result for a TMOS working at 8 Hertz. You can see for the speed precision, we have an error that is smaller than 0.2 meters per second. This is more than enough to actually distinguish between walking, jogging, running, if you really want to go for a classification. And the direction accuracy is of 98, but 36%. You see there's a second column here, which is multiple people. This is basically a problem that you have with current systems, a corner case, where multiple people walk together very close to each other, like tailgating, with a distance less than 1 meter, or also if they're side by side, depending on where you place the actual sensor. There are other ways to solve this, more to this later. So regarding the power consumption, the entire system, together with the processing, the protocol energy advertising, and the TMOS sensor consumes 63 microwatts, which actually shows why we actually went for a self-sustaining device. And interesting is, of course, the very low power consumption for the MCU, since there is no processing overhead. So as a conclusion to this project, using this model technology, two stages of development, we have full characterization of the TMOS sensor, and also showed that we can use this information to create a completely self-sustaining distributed node for contextual intelligence. So here for speed, distance, and direction estimation. And there are still some problems that we're trying to solve. This is actually part of the future work as well. I try to solve it also using like multiple TMOS sensors and also maybe sensor fusion with other sensors. Interesting is also a positioning system. I use 4 TMOS sensors to show that you can actually create a positioning system for one person in a room that is more or less 15 square meters, which is pretty accurate, up to 0.6 meters in error, I guess, if I remember right. But yes, there's a lot to research in this area. And before I open to discussion, I just want to show a small video where I just created this simple device that I showed before for people counting. So you can see that I place a device on the door tray with a solar panel pointing to the back where the light is turned on. I can just connect to it using Bluetooth Low Energy, and information is then going to be advertised given the distance. The distance in the case not, only direction is sorry. And of course, if you have direction of motion, you directly know if there's some kind of people counting where you can just count out and down. Well, that's basically it. Thank you very much. And if you have any questions.